بسم الله الرحمن الرحيم. I am Dr. Abdalrahim from Yوجد department to give a second lecture to third year students. The lecture will focus on the use of spectral analysis and the determination of the structure of natural products. Spectral analysis utilizes electromagnetic radiation as energy source. The type of analysis will depend on the wavelengths of the region of electromagnetic radiation. For example, the NMR will utilize region with wavelengths from 1 to 5 meters. This is the region for radio waves. IR will utilize the region from 2.5 to 15 micron. Visible and ultraviolet absorption spectroscopy will utilize the region from 200 to 800 nanometers. The X-ray diffraction will utilize the region with wavelengths shorter than 10 raised to the power minus 3 micron. Useful types of analysis using this type of electromagnetic radiation include infrared, UV, and NMR. X-ray diffraction is beyond the scope of this course. With regard to IR spectroscopy, we will be satisfied with the previous classes you studied in analytical and organic chemistry. However, in case of UV and visible spectroscopy, we have some types of analysis that will be useful in elucidation of the structure of some natural products. The first is the Woodward-Feser rules for some chromophores such as dienes and enones. The wavelengths of maximum absorption can be determined on practical basis, and consequently we can derive some calculations. The wavelengths of maximum absorption will be affected by the configuration of the diene and presence of substituents of the diene ring system. We have two types of dienes, the homoannular diene and heteroannular diene. The homoannular diene, two bonds in the same ring, has maximum absorption of 253 nanometers, whereas the wavelength of maximum absorption for a heteroannular diene utilizes the region with wavelengths 214 nanometers. The presence of substituents such as ring residues or alkyl substitution will increase the wavelengths of maximum absorption by 5 nanometers. Double bond extended conjugation will increase the maximum absorption wavelengths by 30 nanometers. The presence of exocyclic double bond will also increase the wavelengths of maximum absorption by 5 nanometers. These values, the students is asked to memorize these few figures. However, a further polar grouping are present on the chromophore. We will provide the values of the effect of these additional groups to the students solve the problems, such as, for example, ester, ether, halogen, and amine. In this case, we will provide the student with the value by which the chromophore lambda max will be increased for each group. Here are some solved problems and training for the students. Transitoid ring system here is stands for heteroannular diene. As you can see in this, for example, in this case, we have transitoid or heteroannular diene with 214 nanometers, the parent chromophore. The observed value, which is practically obtained, is also very close about 217. In this example, we have additional alkyl substituents on the diene ring system, which will increase the wavelength of maximum absorption by 15, 5 for each alkyl group in this transoid or heteroannular diene. In the lower structures, we have heteroannular diene ring system also, but present in cyclic structure. In these examples, we can encounter exocyclic double bond, which will increase also the wavelength of maximum absorption by 5 nanometers. Here we have, for example, the transoid with 215, the parent chromophore, ring residues 3, 1, 2, 3. This will increase the wavelength by 15, in addition to the presence of an exocyclic double bond. Therefore, the wavelength of maximum absorption will be 234 nanometer, very close to the observed or the practical value. And in this example, the same calculation can be used. However, the ester group or the ether group will increase the wavelength by 6 nanometers. 6 nanometers, and there is the possibility of 6 nanometers, 440, because of the additional, this example here is more than that by 6 due to an extra ether group. This is due to the effect of an ether group. These are also solved examples from natural products in which these chromophores may be encountered. For example, here we have steroid ring system. Here, this exocyclic double bond is exocyclic to two rings, this ring and that ring, and that's why it is calculated twice. So therefore, we have 3 exocyclic double. When we want to calculate the wavelength of maximum absorption, we have heteroannular diene 214, and we have also ring residues 1, 2, 3, 4, 5, in addition to an extended conjugation to the parent diene. You can calculate yourself the wavelength of maximum absorption as a training for you. The lower examples include examples for some natural products. For example, this is called abitic acid. The parent diene here is a homoannular diene, which has 3 ring residues in addition to 1 alkyl substitution. Additionally, we have also an exocyclic double bond. Therefore, the wavelength of maximum absorption will be 278 nanometers. This is very close to the observed value, 275. In this example, we have tetra unsaturated structure, cyclic structure. We have the possibility of homoannular and heteroannular diene. However, we calculate our wavelengths based on the homoannular diene, which has the larger lambda max. Therefore, the parent diene will be 233 with 2 additional extended conjugation, which increase wavelengths by 60. We have also 1, 2, 3, 4, 5 ring residues, which will increase their wavelengths by 25 nanometers, because in this case, this carbon is linked to 2 unsaturated carbons. Therefore, it is calculated twice. Additionally, we have also an ester group. The ester group has no effect. It will increase wavelengths by 0. Therefore, the calculated wavelengths will be 353 nanometers. These are some solved examples, training for the students to solve this kind of structural problems. The second chromophore talk about the enone ring system. The enone ring system, which has a cyclic enone or six-membered enone, a parent chromophore will display lambda max at 215 nanometers. 215 nanometers. The presence of extended conjugation will increase the chromophore lambda max by 30. However, the F-cyclic double bond will increase also by 5. But the effect of the substituent will be dependent on the site or the carbon to which this substituent is attached. For example, in this acyclic enone, we have the parent chromophore 215. You have alpha methyl group will increase the wavelength by 10. The beta will increase by 12, and we have two beta substituents will increase by 24 nanometer. Therefore, the wavelength of maximum absorption will be 249, which matches the observed value, or the calculated matches the practical value. Here we have cyclic six-member enone, which has wavelength maximum absorption chromophore at 215. The extended conjugation will increase the wavelength by 30. We have also delta ring residue, which will increase the wavelength by 18. Gamma or HER increased by 18 nanometers. However, this enone has homoannular diene. Therefore, I will add 39. The difference between homo and heteroannular diene. Therefore, wavelength maximum absorption will be 302 nanometer, which is very, very close to the observed or practically measured value. In this case, we have five-membered enone, ring system, five-membered enone ring system. Five-parent enone here will exhibit a lambda max and 202 nanometers. Or here, for example, we have parent enone 200 and 202. Additionally, we have two beta substituents. It will increase the wavelengths by 12. And then we have also an exocyclic double bond. Therefore, the calculated lambda max will be 231, whereas the observed 226. In this example, the same, but we have alpha or bromine attached to the alpha carbon. This will increase the wavelength by 25 nanometers. Therefore, the calculated value is 256 nanometers. These are some examples for the second type of chromophore. One additional application for UV spectroscopy in the field of natural product is the use of UV lambda max to conclude or obtain the substitution pattern of a flavonoid molecule. Flavonoid molecule, as you can see, benzo 2-aryl benzo gamma pyrrole or 2-aryl chromone. This flavonoid molecules usually has two bands, long wavelength band 1, that due to the cinnamoyl ring system, the string and saturation and the carbonyl. We have also a short wavelength band, band 2, which is due to the presence of the benzoyl ring system. The UV lambda max of the flavonoid molecule and ethanol, in addition to the effect of some shift reagents, can be used to know the location of hydroxyl groups on the flavonoid monoclonal. For example, you have the rutin pentahydroxyflavone with a sugar residue at hydroxy group attached to number 3 carbon. The presence of also the hydroxyl system can be concluded by shift with for example, sodium acetate and boric acid, or the decrease in the shift of aluminum chloride after addition of HCl. This can be used to confirm the presence of an ortho dihydroxyl system in this type of structure. As you can see here, this shift in band 1 due to addition of aluminum chloride. However, with addition of HCl, this shifting decreased, means that we have ortho dihydroxyl system. Okay, because we have here two one acid stable hydroxy keto and the two diol system, which is a acid sensitive. This will vanish upon addition of HCl. Okay, therefore this compound contains also the hydroxyl system. The presence of 5-hydroxyl group can be concluded by the shift in band 1 upon addition of aluminum chloride. This large shift in band 1 indicates the presence of 5-hydroxyl group. 5-hydroxyl group. And therefore, the aluminum chloride spectrum is the sum of effect of all complexes on the spectrum. Hydroxy keto, this is acid stable, and ortho dihydroxyl acid lowry. And the shift by aluminum chloride and HCl represents all this due to the effect of hydroxy keto complex. Result of C5-hydroxyl and the keto group. This way we finished talking about the application of some spectral data based on UV measurements, and we'll start with the very, very important topic, the nuclear magnetic resonance, NMR. NMR is the most important spectroscopic technique which provides information about the type, number, and relationship of atoms forming an organic or natural product. The theory of NMR is based on the fact that some atoms are characterized by having nuclear spin. These atoms are marked by having either odd atomic number or odd mass number. Odd atomic number or odd mass number, or both are odd, such as, for example, proton H1, proton, which is H1. Here we have odd mass number and odd atomic number. Carbon 13 mass number and 6 atomic number. P31 is the mass number and 15 the atomic number, and 15.7 also an H21 and F19. These types of nuclei or isotopes of certain elements display or are in NMR chromophores. On the other hand, nuclei which has even mass and atomic number are not in NMR chromophore. Therefore, NMR is a phenomenon resolved for some isotopes of certain atoms. For example, carbon 13 H11, H21, H31, F19, B31, N15, and so on. Those nuclei or atoms with even mass number and even atomic number are not in the Mark chromophore. For example, O16-8 or O16 or 18-8. These are not in the Mark chromophores. This is a demonstration for NMR spectrometer. The sample of our compound is placed in an NMR tube and dissolved in nitrate solvent, placed between the pores of a strong magnetic field, and a radio frequency is allowed, which will cause spin flip and energy absorption or energy loss and transition between energy levels. Therefore, the signal can be obtained. This is an example for an FT NMR spectrometer. FT NMR spectrometer or free transform NMR spectrometer. Spin quantum number, which is has a symbol of I, can determine the number of orientations or allowed spin states that the nucleus will acquire in applied magnetic field. Number of orientations is equal to 2I plus 1. I is half here for carbon 13 and proton. I here is a half. That we have two orientations. One energy again, which spin against the applied magnetic field, and the other one is lower energy, which will spin with the applied field. Of course, the proton and the carbon represent the most important examples because they constitute inorganic compound. The NMR phenomenon is not observed in the absence of magnetic field, because in the presence of magnetic field you can observe the nuclei will either be oriented with the field or against the field. In absence of magnetic field, the nuclei will be randomly oriented. Once when we apply magnetic field, there will be two energy levels for protons. It is possible in this case to provide radio frequency which will cause transition between these energy levels and spin flip will happen. And thus we can observe NMR signals. Here the energy gap between this is the direction of magnetic field. This proton, for example, spin against the field. It has higher energy. It's magnetic spin minus half. Whereas this lower energy nuclear spin, aligned with the field and has lower energy. The spin or the energy gap between the high energy and low energy states increased by the increase of magnetic field strength. In absence of magnetic field, the energy gap is zero and we cannot absorb NMR. However, when we increase the magnetic field, will be energy gap, and this allows, upon addition or upon the use of radio frequency, transition between energy levels. The delta E, or energy difference between the high energy anti-parallel spin state and the low energy parallel spin state, is equal to H gamma over 2 pi multiplied by H naught. H is a nuclear constant called Max Planck constant. Gamma is gyromagnetic ratio and pi is mathematical constant. Therefore, this figure of this part is constant. And there is a relationship, direct relationship between the energy difference and magnetic field strength. Therefore, energy difference or energy gap is a function of the strength of magnetic field. The unit of measurement of magnetic field strength is called Gauss, equal to or Tesla is equal to 10,000 Gauss, whereas the unit of the frequency is Hertz. Also, delta E is equal to Planck's constant multiplied by nu, which is the frequency. Therefore, h nu is equal to h gamma over 2 pi multiplied by magnetic field strength. Therefore, this equation can simplify or can be simplified as being nu would be equal to gamma over 2 pi multiplied by h naught, or nu equals constant multiplied by h naught. This is called the Halma equation, very fundamental equation in MR. This equation means that the frequency is not constant value. It is dependent on the strength of the magnetic field. Strength of the magnetic field. And the certain value and this proportion between the frequency and magnetic field strength, energy is absorbed and resonance will occur and a signal is observed. This table contains correlation between the magnetic field strength and the frequency of electromagnetic radiation used for each strength, for proton and the carbon. For example, at magnetic field strength 1.4, we should use frequency of 15 megahertz and for carbon and 6 megahertz for proton. One may ask why the value of frequency is fourfold in case of proton and MR compared to that of carbon, because the gyromagnetic ratio of proton is 4 times larger than the gyromagnetic ratio for carbon, 13. This same ratio is maintained in all the values listed in this table. The ratio between the frequency and magnetic field strength is constant for each frequency. This can also be discussed in this example here. At frequency of 100 megahertz, we need a magnetic field strength of 2.35 Tesla. Any other desired combination should maintain this ratio. Therefore, in MR, the frequency of the absorbed electromagnetic radiation is not absolute value. It depends on the strength of applied magnetic field. Gamma in the equation, as I said before, is called the gyromagnetic ratio. أو magnetogyric ratio is a fundamental nuclear constant. It is a proportionality constant between the magnetic moments and the spin quantum number. Gamma percent constant between magnetic moments and spin quantum number. Since there are two orientations, high energy and low energy orientation or spin state, there will be, in order to observe an NMR signal, will be a slight excess in the low energy condition called Boltzmann excess. This Boltzmann excess is very small, estimated to be 13 protons in the larger energy, larger than high energy at 100 megahertz magnetic field strength, and for 1 million nucleus. This is the Boltzmann excess. 1 for each 200,000 protons, or 13 for 1 million protons. Actually, NMR is a ground state phenomenon because, as we said before, the energy difference between high energy form and low energy form is very small. Acquisition of NMR spectrum. The magnet, as we said before, is a very essential component of an NMR spectrometer, because in absent magnetic field you cannot observe NMR signals. There are several types of magnets: permanent magnet, very old machines, or no field NMR, electromagnets, but in recent machines usually we use superconducting magnets, which provide very high magnetic field strength, and it's cooled with liquid helium. A magnet used in a NMR spectrometer should provide strong magnetic field and homogeneous magnetic field and a stable magnetic field without drifting, because upon drifting you lose your NMR signal in this case. And the NMR experiment will take a long time sometimes. It will continue for several hours. It depends on the type of nucleus you are getting or making an NMR for, either proton or carbon-13. Chemical shift and shielding. Protons will resonate at different frequencies or chemical shift and in the NMR scale, depending on the electronic environment surround these protons. The bond electrons usually generate local fields which usually oppose the applied magnetic field, and this is called diamagnetic shielding effect. Diamagnetic shielding effect. Therefore, any chemical grouping which will decrease this electronic cloud will cause de-shielding of the signal of NMR signal for a proton. The chemical shift may be measured in unit called hertz, but more commonly expressed as bars per million. These two values are interrelated by the following equation: chemical shift in ppm or bars per million equals the chemical shift of the signal from TMS or tetramethylxylate in Hertz divided by spectrometer frequency in megahertz. Therefore, we call it ppm or parts per million, because here we use hertz and here we use megahertz. This is a demonstration for the effect of bond electrons. Here we have the positive charge of the proton. The bond electrons circulate. Circulation of bond electrons generate local fields which oppose or against the applied magnetic field. Therefore, the proton will be shielded or screened from the applied field and will show up or appear with very low chemical shift. There are factors that influence the chemical shift or the resonance of a proton. First factor is the electronegativity effect. Electronegative groups tends to withdraw the electrons, bond electrons, and decrease the screening of the proton from applied magnetic field and cause de-shielding of the proton. Therefore, the presence of electronegative substituent in the carbon-bearing proton will cause de-shielding of these proton signals. Multiple substituents will have stronger effect than one substituent. However, the effect of the use of the presence of a substituent will rapidly decrease by distance. It is not observed for more than 3 carbons away from the proton. Here, for example, a comparison between the methylene protons in case of ethanol and methylene protons in case of propionic acid. The hydroxyl group is a stronger and electronegative group than carboxylic acid group. Therefore, it will possess stronger de-shielding effect of the methylene protons than the carboxylic acid group, and then we can observe that the methylene protons in ethanol are resonating at lower field compared to the methylene protons in propionic acid. Therefore, the more the electronegativity of the group, the less electron density on the methylene protons, the more it will be de-shielded. The second factor influences the chemical shift of a proton is the hybridization effect, the type of carbon to which the proton is attached. Is it sp3 or sp2 or sp? We observe that the more the S character of the carbon tends to bring bond electrons closer to it and thus cause the hydrogen to be de-shielded. Therefore, the olefinic protons resonate downfield compared to the sp3 or protons attached to sp3 carbon. However, upon transfer to the sp carbon system in acetylenic compounds, we observe that acetylenic hydrogen resonate upfield, not downfield, not further downfield, at 2 to 3 ppm. This is attributed to anisotropy effect. This can be explained on basis of anisotropy effect. Also, it is interesting to report that the carboxylic acid proton resonate downfield compared to all other types of protons because of two factors. First, that the OH is electronegative, the O is electronegative, and also the condition of resonance, which will cause the formation of this structure. In this case, we observe that oxygen has a positive charge, and it will allow this proton to be less less sticking to this oxygen. Therefore, acidic protons are de-shielded due to electronegativity and resonance effects. The third factor which influences the chemical shift of a proton is magnetic anisotropy or lack of spherical symmetry. For example, in benzene we have the pi electrons which circulate and generate local fields. These local fields are or have different directions based on according to the molecule. In the center of the aromatic ring, these local fields oppose the applied magnetic field. However, in the region in which the proton or aromatic proton is located, they reinforce the applied field. Therefore, we observe that aromatic protons are de-shielded because they are lying in the de-shielding portion of anisotropic field. Therefore, as I said before, the benzene molecule aromatic protons usually encounter three types of magnetic fields. First, strong applied magnetic field. The second is usual shielding effect due to balanced electrons. The third is the de-shielding effect due to the anisotropic field, which, as we said, in the region of the proton is reinforcing the applied magnetic field. Therefore, we observe that aromatic protons are de-shielded at about 7 ppm, and this effect is due to the ring currents of the benzene molecule. Also, anisotropic field can be observed in case of acetylenic protons. Acetylene protons also here, as you can observe in this molecule, this acetylene molecule, the triple bond or the bi-electron of the triple bond circulate and generate local fields. These local fields oppose the applied magnetic field in the region of the proton. The protons here are located in the shielding portion of the applied field. Therefore, the acetylene proton, which is not expected, are located or are shielded compared, for example, to the olefinic protons, and they appear at 2 to 3 ppm. These are the values for chemical shift for certain protons. We can observe here the chloro substitute and electronegative substitute cause the shielding effect for the proton and methane. The increase in the number of chlorines increase the de-shielding effect. In chloroform, for example, the proton is rated at 7.7 ppm. Olefinic protons are de-shielded due to the sp2 carbon here. And benzene, as I said before, the aromatic protons resonate around 7.56 ppm. Aldehyde proton is also de-shielded by the anisotropic effect, and the effect of the chlorine as a substituent in this example, propyl chloride, decreases by distance. The methyl group appear at 1.03 ppm. Very little effect, whereas the methylene resonate at 1.81, and this one directly attached to the chlorine resonate at 3.47 ppm. The effect of anisotropy is very obvious in the example of C18 aniline. This C18 aniline is an aromatic compound, has two sets of protons. Protons located inside the cyclic structure and those located outside the structure. And those outside the structure are experiencing or are located in the de-shielding portion of the magnetic field and resonate at 8.9 ppm, while the inner ones are located in the shielding portion of the anisotropic field and located at around minus 1.8 ppm. Very shielded. You can also observe the chemical shift of the protons in the remaining three structures and get the impression about the effect of this magnetic anisotropy.